Good evening, guys. Welcome back. I'm re-recording the video for Lab 7 because there were some audio issues with it. So hopefully we're not going to have any audio issues this time, but let's go ahead and give this a shot. So I'm going to share my screen so that we can talk about what's going on with this particular lab. So experiment 7 is one of the ones that's done in a virtual sense. The reason that I say that is because we were given simulators to be able to use with this particular laboratory. So there are two simulators that are going to be used. One is, and actually let me show you where I'm going to find this. So in the 111 shell, we go under content and then exam 2. And we are in redox. And then we're in the oxidation reduction reactions, which is experiment 7. Within experiment 7, you'll see the activity series simulation, which will open in a new window. And then you'll see the cell simulation, which will open in a new window. And both of these are going to be required to look at what you've been asked to look at. Okay, so there are two parts to this particular laboratory. And let me minimize this for now so we can talk about what those parts are. I'll just pull this over here for now. So there are two parts to this. One is to look at the activity series like this to verify that the things that are on this side are more reactive than the things on that side. Okay, so that's what the activity series tells us. Now hydrogen here, I'm sorry. I swear this happens every time I'm on camera, but not any other time. Is H2 is our standard hydrogen electrode. And so that is listed as, and since it's our standard, it is the one that we use as 0. Everything is compared against that. And I'm really not prepared. So give me 2 seconds. Didn't get all my fancy toys set up. So our standard hydrogen electrode is the reduction. So 2H plus 2E minus goes to H2, and that's 0.0 volts. And that's our reduction as written. So that's our standard against which we measure everything. So if it's over here, it's more reactive than that standard. If it's over here, it's less reactive. Now, if it's less reactive, it's not going to happen in a reduction sense. We would see it in an oxidation sense, but not in a reduction sense. Okay. Now, the way that we're going to be looking at this is twofold. So, one, we're going to be looking at the titration that's listed here, and 2, we're going to be looking at the electromotive series. And for the electromotive series, it says fill and label separate clean test tubes with sulfuric acid, copper sulfate, sodium sulfate, and silver nitrate. And then you're supposed to take some zinc metal and add that in there. And there's a data table in here that you're supposed to use to record your observations about what happened during that experimentation. Now, we asked you to make a prediction. Would any of these things occur? What I would tell you is if you're going to do the predictions, you should be looking at either the electromotive series that's in the lab manual. So this guy right here, or you should be looking at the standard reduction potentials for these to see if you think that reaction is going to happen. So what we're going to be doing is looking at each of these reactions. And we're going to do that with those simulations that we have available. Now, what I'm going to do is I'm going to pull this over here so that I can record stuff on top of it. And then I'm going to pull the simulators back over here so that we can talk about those. But one thing that we have to talk about before we do that is what we're actually looking at here. So what you see when you're looking at this is that we have zinc metal and copper metal that we're going to be dropping into these solutions. And these solutions are listed as, in this case, sulfates. Actually, all of these are sulfates, except for that one. That's a nitrate. Okay. The sulfates and the nitrates are counterions that we do not need to worry about. So while they are present, and they are, what they actually do in terms of chemistry is very little, and in fact, nothing. So if we talk about the Zn solid reacting with that H2SO4, I'll go through that one. H2SO4, this is aqueous. And that's going to give us some products. Now, remember that when you have H2SO4 in solution, it's an ionic compound. And so that's completely dissociated. So H2SO4 becomes H2 plus SO4 2 minus. H plus, two of them, plus SO4 2 minus. So that's what you're actually looking at in terms of what's in your beaker. Okay? So that's what you're looking to react against, not this part, because when we go to the other side, we know that this becomes Zn2 plus, and this becomes H2 gas. And I know that because I've done this a million times, so we'll talk about that in just a second. This one is going to be aqueous. This one, of course, is aqueous. So when you come over to this other side, you're going to have the Zn2 plus the H2 gas plus the SO4 2 minus that's present in the zinc solution. Okay, so that goes away, and my net ionic reaction for this is going to be the Zn solid plus 2H plus goes to Zn2 plus H2 gas, because that SO4 2 minus is just a spectator ion. So we don't need to include it. We're writing a net ionic equation for this so that we're looking at only the parts that are involved in chemistry. Okay, so that while it's present and Alex absolutely wants you to include it, it is not part of what we're going to be talking about here, because it's not actually a part of the chemistry that we need to be looking at. Okay, so that's going to happen for all of these. These ions, the sulfates and the nitrates, are not important. Okay, you're concerned about the zinc reacting with the H plus, the Cu2 plus, the Na plus, and the Ag plus. Okay, now the way we do that, and I'm going to start with our standard reduction potentials. We have zinc over here on the left, and over here on the right, we're going to put in our hydrogen. Okay, now what I see when I have this running, which I do at the moment, is that I see from Zn, we're getting Zn2 plus going out into solution. Electrons are traveling up this wire and across over here into this beaker. They're then reacting with that H plus, and those two come together to make H2, which then bubbles out. Okay, so that's what I'm looking at. This is a reaction. This does happen. Okay, so this is something that we would record as actually having a reaction here. And I would note that bubbles are formed. Okay, so that's what I see. So that's how you're going to do the standard hydrogen. And the second time when you do this, you'll change this out for copper and see what happens there. I'll let you do that. Now, the other ones that we're going to be looking at are from here. And so if we want to be comparing that to zinc, we'll go ahead and choose, I wish these were in order, but they're not. We'll choose the zinc, and then we'll look at the next one, which is copper, right? Now, it's spelled wrong, but there it is. And we'll say, okay, run this, and let's see what happens. And as we watch, see what happens there? This copper came up, and it reacted, became part of this, became Cu solid, and the Zn2 plus came off. So that is a reaction, okay? And what you see in the simulation is Zn2 plus in solution, Cu in solid. Okay, because that's what we're observing as we watch this. Okay, so that's what we're talking about. And we want you to make observations for all of these. There are only 4 of them that are actually going to have reactions. We'll talk about that later. Now, the next part that we're going to be talking about is this right here. And I'm actually going to close out these simulators now because that's all you need to do with those. So make sure you make an observation of each and every one of them. Okay. Now, I'm going to close that, and I'm going to close that, and I'm going to move that. Now, where did my Where'd they go? This is the one I want. So in D2L, there is a data sheet that you will find with that, where the simulators are. There's this data sheet, okay? And what you'll see here is it'll talk about whether or not there should be a reaction for the zinc metal, which each of those solutions, okay? You can verify your responses, the things that you observed against the data that's here, right? But the next thing we need to talk about is the determination mass percent of hydrogen peroxide. And that's the molarity of KMnO4, which is actually 0.198, not the 0.2 that's listed in the manual. And then you have a mass of your sample, which is given to you as 1.01. So this was a 1.01 milliliter sample. It is a 1.00 gram per milliliter. So that gives you 1.01 grams for that sample. Each one of them is that. And so, sorry, volume of the diluted sample. I can't remember what the answer to that is. So let's go look in here. Obtain approximately 60 mils, pour 4 to 5. 10 milliliters of the household hydrogen peroxide into a 100 milliliter beaker. We then take a sample of 10 mils of that. So we used 10 milliliters for each one of those. And then there is data that's given to you for the volume that each one took. Okay, so my initial burette volume for this one is 8.4. This is 28.1. This is 4.6 and 24.7. Now remember that your burette is listed from 0 down. So the lower number is actually higher up on the burette. So what you need to do is subtract this smaller number from the larger number to figure out how much was actually used to do that titration. And that calculation goes right there. And where's my calculator? Sorry. So if I take my 28 28.1 minus 8.4, that gives me a volume of 19.7 milliliters that was used for that particular sample. Now, we're going to be calculating the mass percent of H2O2. So that's why it says fill in. You'll need to calculate that as we go through. And this is the information that you'll need to be able to do that. All right. You'll need to balance the redox reaction. Okay. So you should have two half reactions, one of which is your Mn half reaction, and one of which is your H&O half reaction. So split those two, do the balancing just like you always would. You'll need to know that ratio to be able to do this. Now, if I take and do a tiny little cheat, I see that it is a ratio of 2Mn to 5H2O2, and we will need that to do the stoichiometry. So you need to show that balancing. You need to show how that works because it's important that that's included. But that calculation, we absolutely need that value to be able to do the calculations that we're looking at. So that's our pre-lab stuff. Now, they wanted you to have that balanced before you went into the lab. Now, your objective, of course, is going to be on page 46. And we talk about the mass percent of hydrogen peroxide. That is the one that we just did, the one that we were talking about, the MnO4 minus, plus plus the H plus, yada, yada, yada. That reaction, when it's balanced, that's what you want to put here. Assuming the density of the diluted H2O2 is 1 gram per milliliter, calculate the mass of each aliquot used in the titration. Your sample is the 1.01 milliliters times the 1.00 grams per milliliter. And that means that both of these are 1.01 because that's what they measured. We know that that is what was measured in the lab. Now, using stoichiometry and the balanced reaction above, calculate the mass of H2O2 in the dilute sample. Show all of your work. Now, this is going to be based on the stoichiometry for what we did. Now, remember that was a 0.198 molar MnO4 minus. We used 19.7 milliliters. We have to convert that to liters. It's a 0.198 mole per liter MnO4 minus. So that gets rid of the liters. I know that based on my stoichiometry that I cheated with, it's 2 MnO4 minus per 5 H2O2. And that's moles of H2O2. And I want to get to mass of H2O2. So I need to calculate the molecular weight for H2O2. And I have a molecular weight calculator that I use. I think I've showed you this before. H2O2. And that gives me 34.01. 34.01 grams per mole. And that'll give me the mass in grams that was present in that sample. Okay. And so I can do that happy math. I'm not going to do it for you. Now, you need to do that for both of these right here. Now, that sample was taken from the original bottle and we diluted it 10 milliliters to 100 milliliters. So it was a dilution factor of 10. So we need to take this answer that we calculated and multiply it by 10 to see how much was in the original sample. Okay. So that'll tell you the mass that was in your original sample. Okay, that's awesome. So we take our answer. 3B times 10 grams H2O2 in bottle. And that is the mass. Now, your data results table over here says mass percent. Okay, so we need a mass percent. You have calculated here mass of H2O2. That's what the units are going to give you. The moles cancel there, the moles cancel there. There will be grams of H2O2 that you've calculated there. In order to get a percentage for that, we have to divide by the mass of the solution. And the mass of that solution, it can be found in your lab manual. So what it tells you is that pipette 10 milliliters of the diluted household hydrogen peroxide into 30 milliliters of sulfuric acid. 6 milliliters. So 6 mil H2SO4, 30 milliliters of H2O, and then 10 milliliters of the sample, making your total volume 46 milliliters. And if it's 46 milliliters, and it's 1.00 grams per milliliter, and that means that that's 46 grams for the solution. Okay. And just for that part. Now, don't forget that mass is also in it, so you need to take that into account. So you'll need to take this mass add the grams of the H2O2, and then that total gets divided by the 46 grams. Okay. Sorry, no, your grams of H2O2 gets divided by that total. That's what I meant to say. And you'll need to do that for both of them to put that value in here. So that should go right there. So this is the bottle. This is your sample. Even though it's only asked you for grams of H2O2, you need to report the mass percent of the H2O2 in the sample. Okay. So don't forget that. Now, remember, when you do the dilution portion of this, you found the mass in the original sample by multiplying by 10. But remember that mass has now been divided through this whole thing by 146 milliliters. So that will make your calculations for that a little bit different. Okay, so make sure that you take that into account. Now, that should be everything that you need for your pre-lab. And that should take care of your summary. All right. Now, I'm going to take you in and let's talk about our post-lab. So our post-lab for this, write the 4 net ionic reactions observed in the electrochemical series. Okay. So in this data that we were looking at over here, so we had this, we filled it out. We should observe 4 reactions. 4 of them should work. And we know that one of them that worked was that Zn solid plus 2H plus aqueous going to H2 gas plus Zn2 plus. That's the kind of reaction that we're looking for the rest of them. Okay, so make sure that they're net ionic. They don't include any counterions. They are not going to be zero charges, that kind of thing. Now, it asks you, how many did you predict correctly? The answer could be none. It could be all. If your predictions were incorrect, you now understand how you misinterpreted what you did before. So if you made predictions, which you should have, if you didn't get them right, do you understand why they're not right? Okay, that's what it's asking you. And, how can you remember if it's going to work or if it's not? Okay, there are a number of things that I can tell you. One is, where is it in the activity series? So the further to the left, the more reactive it's going to be, so it can react with stuff on the right-hand side. The other thing that I will tell you is that your standard reduction potential for each of these spontaneous reactions needs to be above 0. Okay, so that is one thing. We're supposed to consider Ag, Cu, Na, Zn, and H. And we are supposed to put them in relative order of reactivity. So I need to compare them to this list that is right here. Okay, so what I need to do is find where they all are in the list. So for instance, silver is, no, I can't write on that. So silver's down here. So I would put this down here because, again, that's least reactive. I'm writing it in the same order that it appears in the lab manual. And then I want to find the rest of them and put them in whatever order they appear in that list there. Okay, so that's how I want them to go in there. Now, once you've done that, what they're going to ask you about is what happens with this SR. Now, when you talk about SR, we have to remember that SR is not part of the list that we've been given. So we need to look at a periodic table. And once we've got these things in some kind of order that makes sense, we then want to look at where they actually appear on the periodic table. And then based on those, we should be able to figure this out. So Na is here, Cu is going to be right there, Zn is right there, Ag is one below that, and of course H is all the way up here. So if you look at the relationship between Cu and Ag, that should give you information about what you would expect from SR. So it should be similar to where we expect lower than Na, but Not by much. So look at the comparison between the ones that are lower than the other ones and do the comparison that way. Okay. So you should have information based on which row it's in and which column it's in as to where it should fit in that list. So use the electromotive series to decide if a reaction would occur between each of the following combinations. Now, the combinations that I'm looking at so I can pull up any list. There is one in the back of the lab manual, so you can look at that one. I want to compare Al metal, so I need to find Al in this list, assuming it's in this list. Oh, and no, it's not. Okay, let me go grab the one from the lab manual, because all of them should be on there. So let me. Content. Mm-hmm. Slapping. I'm like, where is it? I can't find it. And if I scroll, I should see guides for spreadsheets, standard reduction potentials. So here's my list. I want to find AL in this list. I was hoping I could search for it, but it's not working. Oh, awesome. Al3 plus 3 electrons goes to Al solid. So remember, since it says Al metal, we need this to be the oxidation. So we're going to be considering this in the oxidative form. So rather than Al3 plus, so what I have from the table is Al3 plus 3E minus goes to Al, and that has a voltage of negative 1.66 volts. We are going to be considering it as Al goes to Al3 plus 3E minus, and that will be a positive 1.66 volts. Okay, so that's what we have to remember there, is that we're going to have to flip it because of what it says. And then we look at the Ca2 metal, Ca2 plus metal, or it's somewhere where is Ca2 plus? Ca. Cobalt CD CR. Of course. And is this what I actually do? Yes. EMF, SRP, electromotive force, which is E cell, SRP, standard reduction potential. So that's what I'm looking at there. And I'm going to come in here and see if I can find Ca. And yes, I'm that old and I need to get that close. And it's not in there either. I know that I found it. Calcium, Ca2 plus 2 electrons. Ca2 plus 2E minus goes to Ca solid. This is a reduction as written, and I'll need to work with it that way because that's what it's asked me to do. So I will need to take these two potentials, those two right there, and add them together. And if that is positive, then it's spontaneous. If that is negative, it is not spontaneous. And my math tells me that that one will be negative. But that's what you need to do for all of these. Now, remember, when you're looking at the Fe3+, Fe3+ can appear in two different ways. So you can find the Fe3+, plus an electron goes to Fe2+. Okay, so we could be considering that one right there. That's the iron 3 to iron 2. But we also see that iron 2 is listed in here somewhere. I found it. I saw it. Oh, there. Fe2+ plus 2 electrons goes to Fe solid. That's iron 2 going to iron. That has its own potential. So if I wanted to look at Fe3+ going to Fe solid, which is what we should be considering, we'll need to sum those two values as written before we use them. Okay, so make sure that you take your Fe3+ plus an electron goes to Fe2+, and Fe2+ plus 2E minus goes to Fe solid. So those two voltages need to be added together to be the one that you want to consider against. Okay. Now for these, I would expect one of those two to happen and one of those two to happen. Whichever one happens, you want to talk about what is the balanced equation and how many electrons are transferred. Okay. So that's what you need to do there. In your titration reaction, that big reaction that we balanced with the MnO4 and the H2O2, that guy, you need to find what is the oxidizing agent. So an oxidizing agent causes oxidation in something else. It is reduced. So the thing that gains electrons are a reactant, that's the one that's the oxidizing agent. The reducing agent causes reduction in something else, so it itself is oxidized. So losing electrons being a product, that's the one you're looking for there. And then you need to list how many electrons that process was. Okay? And that's everything. All right? Now, I hope that is good. If you have any questions, comments, problems, please let me know. I will do what I can to assist. I'm going to stop sharing now. And I will see you guys soon. Thanks.